In our previous examples where we were composing functions, we were given a numerical input. But what happens if we want to compose two functions and we're not given that numerical input? Well, it turns out we're going to follow the exact same process, except that one step has actually already been done for us, because we're always going to use an input of x if we're not given a number. And notice that we already know what f of x and g of x are equal to. So let's break it down and talk about what I mean by that. So suppose that f of x equals x squared plus 3x minus 1, and g of x equals 2x plus 3. We want to find first f composed with g and its domain. Well, remember that by definition, f composed with g is f composed with g of x, which means f of g of x. In our previous example, we first had to evaluate what is g of x, what's g of 1, what's g of 2, and then we plugged that into f. But in this case, notice that we already know what g of x is, right? G of x, we're already told, is 2x plus 3. So what we want to do is to use an input of 2x plus 3 for our function f. And this is where it gets a little bit more difficult, because now we are using an expression or a polynomial as our input, rather than having just a number like 37 or 5. But we're going to follow the same process. We're going to go to f, and anywhere that there is an x on the right-hand side, we're going to replace that x with 2x plus 3. So I have 2x plus 3 quantity squared, not to the x, plus 3 times 2x plus 3 minus 1. So now I'm going to use my special product rule to be able to square 2x plus 3. Give myself a little bit more room here. So special product rule says square the first term, so 2x squared would be 4x squared. Then we're going to take the product of the two terms, so 2x times 3 is 6x, times 2 is 12x. And then we're going to square the last term, so 3 squared would be 9. Here we're going to distribute the 3, so we get 6x plus 9, and then we still have the minus 1. Combine our like terms, and we get 4x squared plus 18x. 9 plus 9 minus 1 would be plus 17. So f composed with g of x is going to be 4x squared plus 18x plus 17. Now we need to find the domain of this function. Well, remember that the domain is based on the domain of the original functions. So since f of x is a quadratic, it falls under that polynomial umbrella. So its domain is all real numbers. Since g of x is linear, it falls under the polynomial umbrella. So its domain is all real numbers. So that tells me that the composition of the two is also going to be all real numbers. I'm sorry, the domain of the composition of the two is going to be all real numbers. So now let's look at g composed with f. Again, remember that the order of the functions does matter, because that's going to tell us which function we're using as our input. In our first example there, we were using g as the input for f. In this example, we're going to be using f as the input for g. So g composed with f is going to be g composed with f of x, which is g of f of x. And what do we know f of x to be? It is x squared plus 3x minus 1. So we're trying to find g of x squared plus 3x minus 1. So I'm going to come to g of x. Everywhere there's an x, I'm going to plug in the x squared plus 3x minus 1. So I get 2 times x squared plus 3x minus 1 plus 3. Distribute my 2, so I get 2x squared plus 6x minus 2 plus 3. So g composed with f of x is actually going to be 2x squared plus 6x plus 1. Notice that that is totally different than f composed with g. And we're actually going to find out later on that if those are the same, if f composed with g and g composed with f are both equal to x, then that means something, that the relationship between these two functions. But we'll talk about that later on, so you don't have to worry about that yet. I just want you to recognize right now that they're not always going to be the same. And the domain, because the domain of both original functions is all real numbers, the domain of g composed with f of x is also going to be all real numbers. Now, in both of these examples, our domain was all real numbers because our original functions had a domain of all real numbers. But I want you to keep in mind that that's not always going to be the case, because when we're determining the domain of a composite function, f composed with g of x, keep the following two thoughts in mind. 1, g of x must be defined so that any x not in the domain of g must be excluded, and f composed with g of x, or f of g of x, must be defined so that any x for which g of x is not in the domain of f is excluded. What that basically means is that we're still going to find the domain of each of the original functions, but then we're going to have to exclude anything that's not in the domain of the input, and we're going to have to exclude anything that causes the input function to result in a value that's not in the domain of the others. So in our next video, we're going to look at an example of where we don't have functions that have original domains of all real numbers, so we can get a better idea of what I mean by this statement.